Let me move to a little bit more complex topic about how exactly routing on the internet works. So before, the protocols we talked before was RIP and OSPF. So those are for inside the network. So those are not exactly for the whole internet, like how everything works outside. But you still need to do the same on a global scale. And as already highlighted, on a global scale, there's a problem of and nobody wants to disclose everything about themselves. So they want to disclose necessary information, but not everything. And for that purpose, people invented so-called BGP protocol. And there is one concept that the core concept of BGP protocol is autonomous system. So autonomous system is something some enterprise network that is entity that have a single control. So inside this autonomous system, you can run some form of intra-domain routing protocol, like a RIP. Nobody really doing this, but a lot of people doing OSPF protocol, and there's also similar to OSPF, there's a ASes protocol that I briefly mentioned before. And we can highlight I think one of the lectures I already mentioned, stub transit ASes. So these things is just a definition of how they, what is their role as part of the global routing. So the stub AS is effectively the end user networks. Anybody who is simply at the end and not they're not in the business of forwarding packets. The networks are in business of forwarding packets, but they just serving their own needs for whatever, like it's a campus or corporation or whatever something. And those stub ASes, usually they just connected to one ISP, but like more and more they're actually connected to multiple networks. And the other one is a transit autonomous systems. So this one effectively service providers, and they are in business of simply moving packets from point A to point B. And there, I think already highlighted before, there are different levels of this transit ASes. There's a tier 2, tier 1, and just normal transit ASes. If I add a little bit more of the structure, so I think in one of the first lectures I mentioned, we talked a little bit about the different types of networks, but there is actually a little bit more to that hierarchy. So yes, we have the tier 1 networks, tier 2 networks, some IXPs, POP, point of presence, IXPs, internet exchanges, tier 2, tier 3, and actual users. So the reason I draw the picture this way is to ensure that there's actually quite a bit of a relationship between these different tiers. There's always some kind of a relationship between one network and another network. It's a provider customer, or it's a peer-to-peer. So it's depending on with whom we're talking. So this relationship will play a very important role in policing, like in the form of who is allowed to route packets through whom, or like what is being announced in the network. Okay, so peer-to-peer relationship is effectively between the same level of networks. So you can have a peer-to-peer relationship between internet users. It's not exactly BitTorrent, just in case. It's just some form of a policy allowing the customer directly communicate to the customer. Similar relationship can exist between tier 3 networks. So it's one network simply have some partner agreement to forward packets directly instead of going to higher level ISPs. And the same thing can happen on a higher level as well. But the fundamental part of our the core structure is you always trying to send the packet towards your provider. So as an internet user, you have a route or a default route towards the tier 3 ISP, and you send the packet there. If that packet is destined to a customer of that ISP or customer of a customer of that ISP, then it will go down. If not, it will go somewhere up to tier 2 ISP. And at that point, again, if the packet is destined to a customer or customer of a customer, customer of a customer, then it will go down back to the tier 3 or directly to the customer as well. If not, it will go finally to tier 1, and inside of this tier 1 they have effectively peer-to-peer agreement between very large networks, and they will know how to route every single packet. Like they will have directly agreement that, oh, this packet needs to go to this network, and this network will happen to be will have the consumer or customer that's responsible for this destination IP address, and it will effectively go down. So the reason I'm mentioning this model of like going to the provider and so forth is for one important reason. So there is a so-called no-valley policy, which means you can always go to the provider once. Like if you reach some provider that knows that the packet is destined to a customer, it will have to go down from that point, like the logical down. So it's a huge network, but logically the packet can only go from customer, network, provider, and then go into the customer. There are a small exception of this. So sometimes you can make a shortcut using peer-to-peer connection, like peer-to-peer relationship, but you cannot have something like shown on this slide. You cannot go from University of Michigan, which is a customer, to the provider Merit, to the provider Cogent, then go back to the consumer or customer Google, and somehow back to the network Merit and to reach the Berkeley. So this one is completely not allowed as part of the policy. And to give you just a little bit of random picture, so this is the picture I stole from CADA measurement. This one just highlights of a number of different ASes and their relationship, like so-called peering agreement between them. So effectively, if you have a peering agreement, you know how to route directly to that network. Either you have like direct link, or you have as part of some internet exchange point, or some other way to actually reach that destination. And as you can see, there is a clearly distinction between core of the network. So you can see the red lines representing effectively tier 1 ISPs. Then there's this blue line, a bluish area, kind of with a lot of connection between different ISPs, which effectively highlights some form of a tier 2. And then we have like on outskirts, there's some other higher level ISPs, and finally there's a lot consumers. Picture is similar to IPv6, IPv4. Obviously for IPv4 we have way more different ASes versus in IPv6 not everybody yet joined. But this picture is from 2015. I hope things a little bit improved since then, but I doubt it has improved that much. So one thing to remember actually when you talking about the routing tables inside the networks, there is a kind of, as I highlighted on the slide, the actual forwarding or routing table is composed of entries that came from different places. So some entries are from the intra-domain routing protocol, so something from OSPF, RIP, or some other network, and some entries came from the BGP. So look, because you still need to route, you still need to effectively route every single packet. Like if it's for inside the network, then you have to know how to route packets inside the network. And if it's something from the outside the network, then you have to know at least which direction to go if you have multiple connections. And this creates a little bit of problem sometimes, but hopefully not too much. Okay, so I already mentioned BGP protocol a couple of times. So BGP is a border gateway protocol. It's an interesting protocol. As some stories saying, it was designed on a napkin in a restaurant, and we still have basically the same protocol that was designed. Obviously, we have a very careful specification, and you can look it up on IETF website. But effectively, kind of the core element, as already highlighted, is so-called AS. And the algorithm that's being used as part of the BGP is this path vector. It's a path vector thing, which has resembles to a distance vector, but not exactly. I already mentioned the BGP protocol a couple of times just to now define what it is. So BGP is a border gateway protocol and is designed for inter-domain routing. So it's between different domains or different autonomous systems. As part of the core concept is this so-called autonomous system, and it is nothing special. It's just some kind of administrative entity. The only special thing that you have to get the assignment of the number, and there's a limited number of those numbers. And the process is quite similar to IP addresses. So you have to be ISP, you have to go to IANA, you have to request, oh, I'm now a new entity, give me AS number so I can participate in BGP routing. That's effectively it. And using BGP protocol, you can effectively obtain reachability to all routes or IP prefixes on the internet. You can propagate your reachability. So if you kind of effectively can announce which prefixes you own and kind of which one prefixes you want to be reached through. There's a few interesting things inside of the BGP, meaning you may receive multiple information and you may decide to act on different prefixes. For example, you may receive that the same prefix announced from this direction, from that direction, from one path and to the other path. And when I'm saying word path, remember I mentioned that so BGP is so-called the path vector protocol, which has some similarity to distance vector protocol that we talked before. It doesn't require knowledge of the complete topology. But instead of just having this number of hops, it's actually included the complete path. So for example, if this calrun is announcing some prefix towards FIU, it always will include some information ES1, ES2, ES3, and then ES2513, and that would be kind of the last part of this announcement. And if FIU for some reason becomes a provider, then it will take that path, whatever 123, 2513, and then will add kind of its own ES number, like 3681, into the path, and will advertise further. But FIU is technically not a provider, so it's normally it doesn't do that. But in principle, it can do that. It doesn't. Nobody stops FIU from doing this. To give a few small details of how exactly BGP works and kind of to compare to the previous protocols. So for RIP, we used UDP. And there is no reliability, so if some packets are lost, there is a mechanism like soft state mechanism to actually keep sending these packets. And if you remember, it's around 30 seconds. OSPF was built on top of directly IP protocol. It's kind of the same logic. There's also no reliability provided. The OSPF tried to build some form of reliability, but still it's a soft state protocol. So even though it's a harder state than RIP, there's no periodic updates that frequent, but in any case, every 30 minutes OSPF generate new update and propagate throughout the network. BGP decided to go a different path, so they actually decided to go over TCP protocol and define basically permanent state. So as long as this TCP connection exists, then this state exists. It's a little bit complicated in the sense that routers not necessarily have to be physically connected to each other. There may be some small number of routers in between, but those BGP routers will define the policy and what exactly is supposed to be announced. And they kind of, as a first requirement, they will establish between themselves TCP connection and will start kind of exchanging the databases, like exchanging kind of I'm requesting database of information from the other guy. I'm processing this, and I may advertise if I'm allowed to advertise some information back to the provider. And this allowed to advertise, I'm referring back to this no value policy, which basically is built on the fact that kind of filtering what you can advertise, what you cannot advertise. And effectively, the advertisement simply means some kind of a promise that you will forward packet. Like so advertisement is saying that's a destination network. Here's the path, including myself, and that's it. And kind of by saying this, I'm the network promises that if I receive the packet toward that destination, I will forward it. That's it. As a network, you may receive these promises from different directions, and in a simplest case or normal case, kind of the basic logic to pick which way you go is based on a smallest number of the smallest path. So this is kind of much simpler metric than OSPF, similar in some sense to RIP, but without kind of limits of 16. Kind of the path can be reasonably large, but a kind of explicit path. And one trick that there is ability for ASes to have, so they have some little bit of control over how long paths they can advertise. So in an ordinary situation without any problems, AS receive information from the neighbor. If it allowed to advertise downstream, it adds its own AS number as part of the path and then advertises. So for example, from ES2 perspective, if I'm looking to ES3 announcement, so ES3 will announce some prefix like 1111. Then the same prefix, if ES1 is the provider for ES2, this prefix will be announced to ES2 in form of ES3, ES1. If ES2 is again a provider to other networks, it will announce the same prefix as ES3, ES1, ES2. So now kind of path is increasing. One knob that the network can do, it can include itself multiple times. Why would it do it? It's a good question. For example, if it doesn't have a preference of not route packets toward destination, but if it still have, it's still telling other network that it can route the packet. Just trying to say that if you have alternative path, please use that alternative path and me only as a backup option. It's not a great mechanism to, not as reliable mechanism to actually control what you're forwarding, but at least it's one of the knobs that the BGP has. There is one interesting complication in the BGP protocol. So BGP protocol, kind of as a whole, is a border gateway protocol, but it also actually comprised of two, not independent, but two complementary parts. So one is eBGP and the other one is iBGP. So eBGP is the one that we actually just talked about, is an external BGP protocol. So this is the one the protocol that announces all those ASes and so forth. And kind of that's what we discussed before. iBGP is something interesting, and interesting in a sense that the network normally don't comprise of a single BGP router. I mean, at the very least, they have a BGP router on the one end, connected to one network, a BGP router on the other end, and so forth. And you actually have to have some form of synchronization between this router in what information they have about external networks, which prefixes they kind of know about internal stuff, and which prefixes they should advertise for the outside. I mean, I just want to highlight the fact of existence of this eBGP, iBGP. Primarily, when we're talking about BGP, it will be about external or eBGP. But remember that there's still this problem of internal synchronization, and it's actually a very complicated protocol. There is several problems associated with this because you really have to keep a consistent state between different routers. Just to highlight, so for the announcement that's been created, they have a concept of path attributes. So effectively, when I make an announcement, there's literally this ES path. It just defines the network and how many different hops or different ES networks this packet is supposed to travel. Not necessarily it's going to happen, but at least as part of the advertisement. Then there is a concept of next hop, and you have to have this next hop in a sense that ES path doesn't really define a router. So it's like on OSPF and RIP, it was about network and a router, network router, network router. In here we're talking about ES numbers, so there still have to be ability to know where you're supposed to forward. So that's kind of next hop business of. And this local preference effectively just to indicate some local decision of how you want to the other AS to forward back. So for an example here, AS3 has two routers, two border routers that effectively two connections connecting with ES4, and it wants kind of say, oh, ES4, please primarily send packet through the AD connection and use BC as a secondary connection. So this one you can express as part of the local preference. Not 100% reliable because it's still ES4 decision to make the decision how to forward, but at least it can influence. There are other parameters that can be advertised, a little bit more complex, some experimental. There are things called community, and if someone knows more about these properties, I would be happy to hear more from you. I already highlighted the policy, and just to kind of add additional element to this one as part of kind of mechanics, how things are operating. Similar to a previous routing protocol, so there is a distinction between forwarding table or routing table that the router is actually using and routing information. With BGP, actually, it's even a little bit more complex than that, because there's we still have the routing table, we still have the routing information base, but there are multiple routing information bases. So there is a routing information base that the router knows about, and there is a routing information base. It tells each individual customer or each individual whatever, either customer or provider or peer. And it's actually have very complicated logic based on this no valley policy that I already mentioned, to select from the whole database what can be announced to a specific peer. And for example, if I'm a consumer to the provider, I'm actually cannot the database to announce back to the provider will be almost zero. Or actually, it will have one entry just for you, because you still need to allow announce yourself. But the rest, you cannot announce that you can reach some network through the provider to the provider. So it doesn't work. And even if you have multiple providers, you still cannot tell the other provider that you can reach some network. So for example, let's say focusing on this X, X will receive effectively complete database of different paths over kind of WABX, WACX, and for each prefix in the world, effectively, it will have two entries. Like in the actual routing table, it will only activate one of these paths. But if you're talking about the complete picture that X will have, like about whatever each subset of the topology, it will know these two separate paths. However, X will only be allowed to pick announcement about X to announce to B to C. And it will not be able to tell, the policy prevents X to tell B that it can reach A through C. Technically it's a valid announcement that it can take. But this no valley policy, the economic model of this policy, prevents X from doing this. To give a little bit of details of why exactly we have this policy, it's a tough question. I think primarily the whole thing is about the economic model. For example, if your customer, where the heck you would tell your provider, like one of your providers, that you can reach the network, so that provider will effectively be stealing your resource that you buy from the other provider. I think that the other provider will be definitely happy to send packets towards you, to reach Google and avoid using the resources. And you're not going to be happy because you're effectively paying money multiple times. So so one part is definitely some form of economic model, but besides the economic model, it's also performance, because obviously provider will have a better reason to have better connectivity to outside world than you as a customer, and saving the actual table size, because every one good feature of BGP is that you have this path, but the bad feature is paths can lead to exponential explosion, because like you have so many different combinations. And with the policy, it's effectively allows you to reduce number of potential combinations that exist in the whole world, just based on those relationships. The security is one of the big questions that I like to bring up. We already saw is kind of non-existent security as part of the RIP protocol. There is a very rudimentary security as part of the OSPF protocol. So I showed you the header that has authentication stuff, but even that one, it's not really ideal stuff. So it allows you to authenticate a router in a system, but it doesn't really authenticate that this router is actually allowed to announce that specific prefix. I hope you would think that for inter-domain routing they fixed the problem, but it's actually even worse than for inter-domain routing. So in reality, what we have today, the system is really fragile. It's becoming a little bit better, but it's not really based on security, but rather some form of policies, some form of kind of relationship between different administrative domains, different domain admins, and some form of filterings. And there were like multiple different accidents, like even recently, where some big prefix was announced by the AS that has nothing to do with that prefix. There are mechanisms that have been developed, but it's still there's tons of problems. And the problems that I can highlight here is one of them is route hijacking. So this is effectively what I just mentioned. There are kind of sometimes it's done for the good reason, sometimes it's done for accidentally, sometimes it's done maliciously. And effectively what you need to do is be part of the global routing system. So have your neighbors, have kind of BGP sessions with your neighbors, and you need to simply announce a prefix with different AS path. Like for example, you can put yourself into this AS path and like skip a bunch of them. And as soon as others will receive the kind of your announcement saying like, oh, your AS path to google.com is very short, then you probably have very good connectivity to Google data centers. So let us send traffic towards you. And if you have effectively way to reach Google, then you will serve it. But if you like an accident in 2014, I did this intentionally. They did it intentionally for the purpose of like constrain Google within the Turkey, but kind of the BGP system is global, so they affected much bigger population of the network, not just the Turkish ISP. It's similar to what happened in Pakistan in 2008, and there are similar accidents keep happening over and over again. There are a few other interesting things that in existence. So, for example, this announcing unused prefixes. So some prefixes, even though I already mentioned IPv4, we don't really have kind of RIRs don't have any more prefixes to allocate. We still have some prefixes not really used all the time. So there are some prefixes that appear, disappear. Sometimes it's a legitimate reason, like ISP is actually doing that, but there are not so nice people who are trying to send a lot of spam. And to send spam, you have to be part of the network, you have to have IP address, like at least source IP address, and you have to receive incoming packets, in order simply to establish TCP connection. So what they're doing, they're just trying to pick some prefix that is not yet announced anywhere in the world. They quickly join the network, they announce this prefix, kind of appear on the network as a source address, so they can receive packets back and forth, or send and receive packets. Then they start sending a bunch of spam, and then they shut down all this operation, and then pick different prefix and start announcing, pick different prefix, start announcing. So it's kind of, for this part is actually hard to track them, because sometimes you can kind of put some filtering based on IP address, but when your IP address is like the bad guy's IP address is changed, you cannot do really much. And something similar they do with unallocated ES numbers for different purpose, but kind of the same concept. They just pick in the number that was either not yet allocated or was allocated but not actively being used today, and they just announcing something as part of this using this ES number. Again, this is really hard to trace all these things. So I give you one website on this slide, and I'll try to go over it. So this is just a system that was developed in UCLA a while back. So this one is just trying to get access to this BGP information and a little bit process it. So you can explore this site a little bit. I'll try to look up some of the information. It's not updated too often. It's a kind of a little bit dead project. But at least you can get some understanding of which prefixes announced by whom at which point of time, and get some of the history. So it's taken a little bit of time. Oh, and it actually didn't work properly. But try to explore the system, and maybe it would work at some point. Okay, so it's, at least for this part it worked. It's just a basic system. So one random stuff you can do in this system is to look up the ES name. So this is how I figure out what is the ES number for FIU. So this ES3681 is a FIU network, and you can come up with different. You can look up different numbers. Some elements of this site is not exactly correct. So for example, you see this long name, long ES number. There is a history behind this. So normally ES number will like just I think it's with 2 bytes. So that was kind of traditional ES number. However, 2 bytes is only like 16,000 ES numbers. To some degree, it was working perfectly well until a certain point, and then like you effectively ran out of all those numbers. Okay, not 16,000, but 3,200 numbers. So they extended the numbers to have, I think, 4 bytes now, but they did it in a special way, so the representation is slightly different. So it's actually some number dot some number, kind of to avoid kind of some resemblance to IP addresses, like with this dot notation, but just the 2 numbers, just to simplify writing stuff. So with the website that I put here, you can just do some exploration of routing table. There is another website that contains the archives of BGP. So this one, and for the different RIRs, they actually have several ones. So the one that I was a little bit participating with was route views. So that's a US kind of US system, which effectively just based on the University of Oregon. And what it's trying to do is trying to peer with as many BGP system, as many ESs for the purpose of collecting their kind of RIR that they will announce to the customers. And using this information, they can kind of effectively collect archives that can be used by researchers. For example, this Cyclops project that I just showed you. For the purpose analyzing like historical perspective, what has been, like what has existed in the past, and so forth. So there's a lot of information is stored. If you explore, so this one is just literally binary archives. So some of them started 2001, but that's actually quite recent. I think the real ones start way earlier than that. Again, I'm just randomly clicking. Again, this is something recent. I haven't seen this before. Let me check this one. Yeah, still it sounds like there was something in the 90s, if I remember correctly. Okay, but I somehow cannot find anything useful. I mean, it doesn't matter. Okay, just you can try to explore. So this one doesn't really give you any information unless you know how to process all these MRT files. No graphics. Cyclops give you some additional graphics. Similar archives exist for the RIPE, which is European RIR, but I'm not going to go in that detail. I just know that there are some archives. This is kind of those archives not really needed for the functioning of the internet. It's more like for the research side to try to understand behavior over long term. One thing that just want before I finish, for the security perspective, as I said, there are several solutions that are in existence, and they work in slightly different directions. So one kind of direction is to secure BGP sessions. So all BGP sessions technically are already secured. So in order to kind of establish this session with your neighbor, you have to have agreement with the neighbor. You have to have some crypto material to actually communicate with the neighbor. So that's kind of covered. But just securing the session, like email, it doesn't really secure the content itself. So you still, even the session is secured, you still can accidentally announce something bad stuff or receive something bad stuff and then do the wrong processing. So the direction in one direction, they try to secure the whole ES path. So like every ES in the world have its own crypto material, and whenever they add something, like try to make an announcement, they created a kind of signature on top of all they received. And this is kind of secure BGP proposal. It's not actually deployed. For one reason, it's a little bit too complicated, because of this ES path property, you actually have to sign the signed information. So every time someone adds an item to the ES path, it actually have to sign the whole thing. So it's become kind of onion signature, the signature of the something more, signature something more. It's ultimately very good mechanism because you can verify everything, that the path is valid, that the guy who added the ES path is valid, but it's just kind of complicated. Plus, it still doesn't really address the problem, because you can add yourself, you can still create the route. There's no mechanism to actually check whether you own the prefix or don't own the prefix. Effectively, the securing the resources. If you have been allocated ES number, or if you have been allocated a certain prefix, you're receiving a certificate associated with those IP addresses. And when you make an announcement, you effectively trying to kind of include some form of signature related to that announcement. Again, it's better than nothing, but it still does not completely solve the problem, because to completely solve the problem, you actually have to have a secure BGP and this mechanism, but there is several technical issues that exist in a system that prevents doing this. Okay, so that's probably it. I wanted to talk about the BGP protocol and the internet in general. We'll probably need to talk a little bit more in person, of at least understand what is your current understanding of the whole system. But for the routing, just remember, there's a concept of intra-domain routing, like something inside the ES, something inside the domain name, or something inside the network domain. And there's a primary protocol for the inter-domain routing, which is BGP. I mean, OSPF, you know how it works. RIP, I hope you also remember how it works. Remember the some timing associated. Remember how can you at least estimate the number of messages in the system being generated. So it's kind of important element of the protocol. And for BGP, again, remember that it's running on top of the TCP. It's reusing the multiplexing reliability. It's basically using some form of a hard state for the lifetime of TCP connection, because when TCP connection breaks, you know that the other node doesn't have the same state, and whenever you reestablish the connection, you resynchronize the databases. And BGP actually contains two parts. One is eBGP, iBGP. iBGP is something to exchange information of BGP routers inside the same ES, because it's kind of important to synchronize, important to announce the proper stuff to different locations. And eBGP is what effectively we're talking about, is external BGP protocol, all about those ES numbers, properties, and so forth. Okay, I hope it was interesting, and hope to see you soon in class.